So before we get on to some examples of how to compute line integrals, I just wanted to talk a little bit more about the interpretation, because a lot of times when we cover this material, students are confused by like, what actually does this thing mean? What am I doing here? So first recall that the arc length element, ds, is the speed of the path times dt. And then when we integrate that against 1 over the curve, we just get the length of the curve, right? And so this is one way actually of thinking about like what you've seen, even if you're just back. So if C is actually a curve in R, so it's going to look really boring. It's just going to be a line segment, but that's fine. You can still do it. Then the integral from a to b of x prime of t dt, that's just another way of talking about the integral from a to b of dx. I'm just using chain rule kind of backwards, right? And so then when you integrate a derivative, you just recover the variable. And so that's from a to b. And so when we evaluate, we go from b minus a. And you can see that that is, in fact, the length of the curve from a to b, right? Okay. So let's do something maybe slightly more exciting. First basic example. Let C be a circle of radius A. Okay, so then the standard parameterization would be to do C of t is cosine t sine t, for t going from 0 to 2 pi. And, or I guess most of the time I've written this in this format, so maybe I should stick with that. And so as soon as I write down this parameterization, and this is going to be super important for all the stuff that we do later on, you write down a parameterization, and then this means you're going to make the substitution x equals cosine t, y equals sine t, because that's exactly what this means. This is your x coordinate and this is your y coordinate. So you're setting up for doing a substitution. That'll be super important later on. Not so important right now, but later on. Oh yeah, big time. So let's see. So we look at the derivative of this one and we get minus sine t cosine t. And so then our speed is going to be square root of, oh, silly me, this was supposed to be a circle of radius a. Whoops. Okay. Fix. Okay. So this is a, and now it's okay. Sorry about that. Okay. So let's see. So now we've got minus a sine t quantity squared. That's my x prime squared. And then I've got my y prime squared. So that's this guy. And that's just a, right? Good old Pythagorean theorem. Sine squared plus cosine squared equals 1. All right. So then when we go to find the length of this curve, it's going to be the integral over our parameter domain, which is this one right here. So we have the integral from 0 to 2 pi times our speed times dt. And so that's just 2 pi a, which you know is indeed the circumference of a circle. So it's always nice when you get the right answer at the end. So one way of thinking about this, so if we've got this just the integral over a curve of 1 ds, then we get the length. But most of the time we're going to be doing more interesting things, like looking at the integral of f ds. So what does this equal? Well, like I said last time, this is like what would happen if you were not talking about just the length of the road, but how much gas it took you to traverse the road. So for example, suppose we had some function like this, And so I've got the same curve C here down in the plane, and we can imagine it being parameterized by good old cosine t sine t, just as before. Only now you've got this function. So here's f, the graph of my function. And so if I'm looking at the height up above here, that's telling me something about how much fuel I'm burning. So apparently, like during this part of the journey, maybe it's close to driving on the flat, but over here where it's up real high, maybe that's a place where it's we're going up a hill. So let's see. So this is gonna just connect some lines over here, so you can kind of see how it follows along. And in the back. Oh, come on. Come on, dumb app. All right, it's not loving me anymore. Okay, here we go. Good enough. All right, so this is as we're traipsing around, following hill and dale over some function. So now here's another more physical idea that you could use to conceptualize what this the value of this integral is. Suppose this is a fence, and you've pinned in, I don't know, a small child that you're babysitting, or a dog or something, and so I'm just gonna like paint in the sides of the fence here with green paint. Well, what's the surface area of this fence with this crazy top that's been, I don't know, looks like it's been attacked by some deranged guy with a jigsaw? Well, the surface area of this fence that I'm painting in here, that's exactly going to be given by that integral. Maybe I'll paint the back part of it. Oh, wrong pen. Let's go make it slightly blue. There we go. Okay, so how much paint is it going to take to paint this crazy fence that looks like somebody tried to make a roller coaster out of the top of it? Well, it's going to be the integral over the curve of f with respect to ds. That's going to tell you how much paint you're going to need. Okay, and I'm losing interest in coloring this stupid thing. It's going to be ugly, so I'm just going to let it be ugly. All right, there we go.